Hey there, my name is Alejandro, and welcome back for day 4 of me doing the Daily LeetCode challenge until I hit 1 year's worth of green contributions here on GitHub. So let's get started right into it. Today is July 19th, 2024, and yeah, here we go. Let's see. Okay, LeetCode medium. Let's read this. Problem number 1605. Find valid matrix given row and column sums. Okay. You're given two arrays, row sum and col sum, okay, of non-negative integers where, okay, so, positive or zero. Integers where row sum I is the sum of the elements in the ith row and col sum j is the sum of the elements of the jth column of a 2D matrix. In other words, you do not know the elements of the matrix, but you do know the sum of each row and column. Find any matrix of non-negative integers of size row sum.length times col sum.length that satisfies row sum and col sum requirements. Oh, it's kind of like Sudoku. First thing that comes to mind is backtrack algorithms, but I've never actually written a backtracking algorithm. Return a 2D array representing any matrix that fulfills the requirements. It's guaranteed that at least one matrix that fulfills the requirements exists. Okay, yeah, let's see an example. So 3, 8, and 4, 7, right? So yeah, that sums to 3, that does sum to 8, that does sum to 4, that does sum to 7. Okay. This is going to be interesting. Okay, very first thing we can do is we can create a matrix that's of the size of the dimensions, right? So row sum.length times col sum.length, right? So matrix equals 0 times, oh, I forget which way is the times let's hopefully get one that's not square. Are they all going to be square at the beginning? Okay. Row sum I in range length col sum length. Return matrix. What? Length, yeah. Length of row sum. Yeah, okay, it just confused me that they put row sum.length in this, and so, okay. I'm coding in Python. Yeah, so let's do, I want to get a test case where, man. Times length row sum. So this will be the length of the inner arrays. Three by 4. So this should be col. Okay, either way, I'll just have to flip them at the end of the day. Okay, so let's think about it. The first thing that comes to mind is that we could go element by element, and yeah, this is making me think of backtracking, but I don't know how to implement the backtracking algorithm. I learned of them in my AI course, but I don't know how to actually. Okay, we can still figure this out. Okay, you're given two arrays. Okay. Yeah, DP is going to be way too inefficient. You have to be. Can I do this greedily? I could do something greedy where it's like I find the row with the current smallest sum and the. You know what? Let's do that. This is a solution that is very brute forcey but could work. So let's get the index. We're actually gonna do what we did yesterday. Get min index. actually, we're just gonna call this argmin. Self comma r for min element is equal to float of infinity for I in range length r. If r of I is smaller than the minimum element, then result index is equal to -1. If r of I is less than the minimum element, then index becomes this new I. Obviously, we update minimum element to become r of I. Return index. Argmin just means like, so like if there's a minimum element in the array, well, it's going to be at some index in the array. Argmin is just like, okay, give me that index and so on, like kind of like argmax. So we're just going to do the same thing for argmax. This is going to be max element. I don't need to rename, but it's just good practice. If ri is this is going to start off as negative infinity. There we go. Okay, sweet. So this is going to be a very brute forcey solution. So do I want argmin or argmax? So I'm trying to think. This row sums. If I get the one with the smallest sum, argmin row is equal to argmin row sum. Sum equals 0. Total sum equals sum of row sum plus sum of call sum. So while in range length total sum. No, not. Oh, this is a number. Okay. Argmin row, argmin call equals delta argmin call sum. Rows, these are indexes. Row index, call index, call sum, call index. Okay. Now we're going to say matrix of row index, column index, plus or equal sum to add, curse sum plus or equal sum to add, return matrix. I wonder if something like this would work. No. So what did I return? What in the heck am I doing? Oh yeah, I need to, oh my gosh, okay. Yeah, I need to subtract these values. So row sum row index minus or equal sum to add, row call sum call index minus or equal sum to add. Okay. Uh-oh. Infinite loop, huh? Why? What's wrong with loop invariant here? So total sum equals the sum of these two. maybe I should, yeah, do arg max. Let's just try this. That's also gonna fail. Max here isn't, because I don't want to grab the max because I can't subtract that from the row sum. It just doesn't make sense, yeah. Okay. But instead of trying things, let's try to think about this. Okay, so row index, yeah. Self to argmin, so on. Print, okay. Row val, call val is equal to row sum, row index, call sum, call index, right? So let's just simplify this. Let's just simplify this. Now we have to actually update those values. Matrix. So the idea is this, right? Like row sum. So like, for example, here we get the minimum value here, which is 3. We get the minimum value here, which is 4. Then we say the minimum of those two values is 3. So it's like, okay, at index of wherever we found this 3, which is 0, index where we found this is 0, and so on, we're going to add that value, which is 3, right? And here it's going to, well, the answer is 3, so that's good. And then we update this to be 0. So the idea is that row sum now equals 0, 8, and call sum equals 1, 7. So now if I get the minimum again here, okay, as soon as I hit a 0, so what I need to do is non-0 and Ri greater than 0. That's what I need to do. Still infinite loop, huh? Did I do this right? And yeah, okay. And Ri start this off at 0. No, that's not gonna work. Okay. Wait, yeah. If Ra is greater than 0 and might as well do this, but like I really want to assert that. Assert Rvi is greater than 0, essentially. Okay. Let's think about this. Argmin non-zero now is going to give me 8, and this is going to give me 1, right? So right now we have matrix is equal to, it's going to be this. Now this value is 3. This value is 0. We initialize everything to zeros at the beginning. Okay. So let's think. Now we're going to get this argmin, which is going to be 8. This min, which is going to be 1. And we're going to say, okay, 1 is the smallest. 8 and 1 here. So this is index 1 and index 0. So 1, 0. Or should I? Okay, so clearly that's not where I should be doing it. Maybe it should be, but that's not why it's going to be breaking. That's not going to be the reason. Of course that's not going to be the reason. But this is where I need to be putting it. This is where I need to put the 1. So, okay, let's make sure. So we have 1 and 0. So if I put a 1 and 0, So that will be, yeah, index 1, 0. So this is correct, yeah. When I run the test, I'll basically get like an index out of bound error if this is incorrect anyway, so it'll be fine. I don't have to think about that too much for now. Yeah, to do verify if should be blank call sum then row sum, or vice versa, just for later. Okay, cur sum equals 0. So I'm always adding this value to cur sum. Row sum, row index, call sum, call index, matrix row. It's very interesting. This should not be time limit exceeding. Okay, well, that's why we're running through this example, right? To see why it would time limit exceed. 1 is what we did, and now we're going to update this value to 0, and we're going to update this value to 7. And now we're going to have 7 and 7, and we're going to take the min of that, and we're going to add that into here where it's 7, and now this is 0 and this is 0. And so cur sum is essentially equal to, we added 3, we added 1, we added 7, which is equal to 11. And total sum is equal, this is going to be the issue, 3 plus 8 plus 4 plus 7. Which is way larger. This is 11 plus, yeah, because like we're not accounting for the double counting of stuff. So yeah, this is an incorrect condition here. I can't be doing it like this. I just one exit condition is when these are both 0. I could do something. I could be cheeky. Actually, I can keep track of something like this. Row sum equals sum of rows, right? Column sum is equal sum of column sum. While cur sum, I can even get rid of this for now. This doesn't matter. While row sum plus column sum greater than 0, this, and then we're going to do row sum minus or equal sum to add, call sum minus or equal sum to add. There we go. Hey, I didn't even need backtracking. See, confidence. Okay, I can't get too overhyped here. But yay, okay, I worked out that example. I might even keep this just for the explanation part at the end, so let's just keep this down here. Okay, let's do a little bit of code cleanup. Oh, okay, yeah, let's run this first to see which orientation it is. Okay, it was this way. If I do row sum and column sum, it'll likely fail, won't it? 75% is great. Yeah. See, this is what I mean. I'll get an index out of range error anyway, so it'll be very easy to check. So this is the correct orientation. We did not need our max and so on. I think the greater than 0 check here was still needed. That is something that we nicely debugged. If I take that off, I think we fail. Yeah. Very nice. Oh, well, we fail for this reason. So let me comment that out. Yeah, infinite loop, exactly. It's just gonna get a time limit exceeded. Okay. So that was not a wasted effort. The only thing that surprises me though is I was gonna do some optimizations to my code, but I saw 75% passing, which means that we're likely to have we're beating 72%. Okay, no, this is weird. Okay, so there's clearly like some sort of optimal solution here that I'm missing. Let me think what it could be. So I build the matrix. This building of the matrix is going to have to happen no matter what. This row sum, this is just O of n time. This is okay. While this, yeah, at least I'm decrementing by sum to adds. Row index, column index. I could fit, I don't, it's okay. Sum to add, that's the important part of the code. This, then, yeah, this is important for the next iterations. Yeah, I gotta add this, and this is the loop invariant. Return matrix. I'll get rid of this business for now. Okay, that's pretty much it. That's the solution I want to upload. 74%. Okay, sweet. Okay, well that's it. Well, I kind of explained what I did then. I'll reuse the example that I used here. So the idea is this. So we want to reconstruct the matrix from scratch, and we only know the sum of the rows and the sum of the columns, right? Or okay, sum of the rows and then sum of the columns. And so my idea was this. Okay, we need to find the elements of this matrix and so on. So why not start off with a matrix of the dimensions that we have? Let's use this example here, right? Where the row sum is this, column sum is this, they're both length 2, the matrix is size 2 by 2. Okay, so we start off with a matrix that's of size 2 by 2. So I'll just reuse the example here I had. We're going to start off with just zeros. Okay. And so on. And the idea is we're going to fill up these elements, right? These elements likely have to be positive. Or like, if there is a solution, why not just use like positive values? It's okay. So the idea is this. We have this row sum. Row sum equals 3, 8. Column sum equals 4, 7. So my idea was this. Why don't we take these row sums and col sums and kind of like distribute the values of these sums to elements? So it's like we need to find some element in the matrix, augmented it by some value, and then now that we know that it has that value, we can decrease the value, the corresponding, like that position in the matrix will belong to some row and some column. So obviously, like if we change this element to 2, for example, well then we know that the sum of this row we just augmented by 2, and the sum of this column right here we just augmented by 2. So instead of my row sum and col sum arrays, what I'm going to say is like, okay, I'm going to subtract. So what is this? This is index. Let's make this easy. Let's say I add 1 here, right? This is index 0 and 0. So I'm like, okay, in the 0th row, I just added a value of 1. So the remaining sum that I want inside of this row is now going to be 2, right? Because if I add 2 more in terms of value to this row, well, then I'll have reached the initial 3 that I wanted. And inside this column, I just augmented its total value by 1. So I want to take this 4, which is the respective column, and decrease this value by 3, because that's the remaining amount I want to add into that column for the rest of the problem. Now, a little shortcut that I realized is like, okay, we could do this just like this, like add 1 to a certain element in the matrix, reduces things by 1, and that, and so on. One thing I was realizing is like, okay, why don't we find the most constraining value between the row sums and the column sums, right? Where it's like, if we're gonna have, if we could pick any element and so on, why don't we pick the ones with like the tightest restrictions, which will be like the row sum with the smallest remaining row to add value left, and the col sum with the smallest remaining sum to add, and so on. Because like the thing you don't want to do is, you know, pick something like 7 here, add it to a random position in the matrix, and all of a sudden realize that the corresponding row only had a value of 3 left, and so on. And then when you update it, this will be -4 and this will be 0, which is great here, but like this is obviously not great because like this row is now like its sum is like too big by a factor of 4. So that's a problem. So we're gonna pick the most constraining ones, which will be the row with the least amount to add in terms of its remaining row sum, and same thing for the column. And that's kind of why I pick like here the argmin non-zero, so the smallest value in each that isn't a value of 0. Why non-zero? Well, think about it. If a row sum's remaining value to add is 0, that means there's nothing more that I should be adding to it. I should not be touching that row. So I want to specifically get the minimum, the most constraining one, whose value is not 0. 0 basically means it's done. There's nothing else to add. So now that we understand that, I come through the minimum here in row sum, it just happens to be 3, and in col sum here it just happens to be 4. Now this is index 0 of row sum, and this is index 0 of column sum. So if I pick element 0, 0 over here, and I augment it by 1, then I know I can remove from these two. But why do just 1 when you can do the minimum of these two? Now if you do the maximum, let's say we do 4, then here we'll do 4 minus 4, which is 0, and 3 minus 4, which is negative 1. This is a problem here, right? Because we over added into this row such that now if I do this, it's too huge. We want the value of this row to be a total of 3, and we have a value 4, which is no bueno. So instead, we have a value of 3 and 4 here. We're going to subtract the minimum one, right? Because if you subtract the minimum one, that means one of them will go to 0. And the other one, it may or may not be 0, but at least it won't be a negative value. And we have to like subtract, go on. And that's why I thought there was like backtracking in my head and so on. But turns out it's not needed. So we just subtract the minimum. So here we'll subtract 3 minus 3. The minimum is between these is 3. So 3 minus 3 is 0. 4 minus 3 is 1. And obviously the actual amount that we add here is 3. So now the sum of this row is 3, which is why the remaining sum that we have to add for that row is now 0. And same thing for this column, where the remaining value that we have to add to this column is a total of 1, because we want its sum to be 4, but its current sum is 3. And then we just repeat this process. So we take the argument that's not 0 from row sum. So in this case, there's only one option left. It's this value of 8. Same thing from column sum. So now it's like this is index 1 in row sum and index 0 in column sum. So we go to index 1 of the rows, the second row, and index 0 of the columns, which is just the very first element. And then we say, okay, let's take the minimum of these two, which is 1. So let's add 1 here. Let's subtract 1 here. 8 minus 1 is 7. 1 minus 1 is 0. So this column now has a value of 0 to add, because its total sum, 3 plus 1, is 4, which was the original, which is the original column sum over here that we wanted this column's value to be. And then we just repeat the process one last time here. Smallest here is 7, smallest here is 7. We remove 7 from both sides here. This happens to be index 1 of row sum, index 1 of column sum. So we come to index 1 row and index 1 column at that value of 7. Bada bing, bada boom. We find one like this one. This row sum is 8 as we wanted, because it used to be 3 and 8. So this is 3. Yep. This is 8. Yep. We wanted this one to be 4. 3 plus 1 is 4. And we wanted this one to be 7. 0 plus 7 is 7. And that's the whole spiel. So that's kind of how the algorithm works. And again, if you made it this far with me, thank you so much again for watching, or whether we were struggling alongside me or so on. I really, really appreciate you for your time. And yeah, that's it for me today. So thank you so much, and I'll catch you next time. Ciao, ciao.